Hello everyone, welcome to the Electron Flow Academy. So our next topic is AC through the inductive circuits. Okay, so in our last class we have discussed about the resistive circuit. Okay, so today we are going to find out what will be the response of the inductors when it is connected to the AC voltage source. Okay, so here we know that our input voltage source equation is like that Vm sin omega t. Okay, so I can rewrite this voltage in terms of RMS value Vm by root 2 at an angle of 0 degree. Okay. So this is our voltage equation. So this is my equation number 1. Okay. So we know that when a voltage is applied across inductor, current I starts flowing. Okay, here the current is I start flowing, and relationship between the applied voltage and the current is given by the expression. Okay, the expression is that V is equals to voltage is equal to L di by dt. Okay, so we can rewrite this equation like V dt divided by L equal to di, or we can say that d of I is equal to, we know that we have voltage source Vm sin omega t divided by L into dt. Okay. So in order to solve this equation or evaluate the value of I, what we are doing here, we are integrating the both side. Okay, integrating both side. So we will get now the I is equals to E m upon L integration sine omega t dt. Okay, so we know that the integration of sine theta is equal to minus cos omega t. Okay, so here our actual value of the current is now I is equal to Vm divided by omega L. We are writing the value of inductor is equivalent to the omega L. Okay, and we know that the minus cos omega t we can rewrite like sine omega t minus 90 degree. Okay, or value of the current is equal to Im. So this value is equal to Im. Im sine omega t minus 90 degree. Okay, this is our equation number 2. So here you can see that in the equation number 1 of the voltage, angle is 0 degree, but in the case of the current, angle is minus 90 degree. Okay, so actually the value of the current is now Vm divided by again omega L at an angle of minus 90 degree. So here you can say that the Im is nothing but here Im is nothing but the Vm divided by omega L is maximum value of the current. So in this expression, the term omega L is similar to the resistor. Okay, we know that in the case of the Ohm's law, I is equals to V by R. Okay, so here in our case, when we have connected the inductive load, the value of the omega is load is equal to omega L. So here we can rewrite that omega of L is equal to Vm upon Im. Okay, so the term omega L is called inductive reactance. Inductive reactance. Okay, this is very important thing. Inductive reactance. Okay, so it is represented by XL. X of L is equal to omega L. Okay, so it's a unit. Its unit is in ohms. Okay, unit is in ohms. It is a measure of opposition to change in the current through inductor. Okay, what is this? This is the measure of opposition to change in the current through inductor. Okay, so next we can see that from equation 1 and 2, we can see that from equation 1 and 2, it is clear that the pure inductance current phasor lags the applied voltage wave by minus 90 degree. Okay, so by minus 90 degree. So if I draw the waveform or the phasor, the phasor will look like that. We have the voltage at an angle of 0 degree. This one is our reference. So from the reference, the current situated at the minus 90 degree apart from the voltage. Okay, so this is the phasor representation. Okay, so if I talk about the waveform representation, we can see that this is our voltage waveform, which is starts from the 0. Okay, and from minus 90 degree, we have the situated the current waveform. Okay, like that. So this is how we can elaborate the waveforms and the phasor diagram in the case of the pure inductance. Okay, so it is clear from equation 1 and 2. Okay, equation 1 is that Em sine omega t, this is our equation 1, and I is equals to here Im sine omega t minus 90 degree. This is our equation number second. Okay, so it's clear that in the the case of pure inductive current wave or phasor, it lags the applied voltage wave or again phasor by 90 degree. Okay, so this concept is applicable for pure inductive circuit. Okay, so our next step is to evaluate the power relation. Okay, so power relation. Okay, we know that the P is equal to V times I. Okay, so power is given by V is equal to Vm Im sin omega t multiplied by sin omega t minus of 90 degree. Just what I have done here, I am putting the value of voltage and current in the terms of equation. Both value I multiplied. Okay. So its value is equal to negative of Pm Im divided by 2 sin 2 omega t. Okay. So what will be the average power in that case? Okay. So we have to calculate the average power. Average power. So average power over a one cycle. What will be the average power? Let's see. So we know that the average power formula area divided by time period. So for the one cycle of time period, we are taking 2 pi, okay, and integrating from 0 to 2 pi, okay. What we are integrating this expression, okay, expression of p. So here we get the negative of Vm Im divided by 2 sine 2 omega t d omega t. Okay. So if I solve that expression, I will get the average power is equal to 0. Okay. So in the pure inductive case, the value of the average power is equal to 0. Or we can cross check this by waveform representation. We can see that the voltage is starts from the 0 like that. Okay. This is our till 2 pi is one cycle. Okay. And the current waveform is starts from the or lags by the 90 degree from the voltage. So it starts from here like that. Okay. So power is equal to V times I. So if I multiply that value and that value, I will get in that case of the negative power. Okay, this is our negative power because in that region from 0 to pi by 2, the polarity of the current is negative. So if I multiply this negative current with this positive voltage, I will get the negative value of the power like that. Okay. And then again in that region from pi by 2 to pi, both the values are positive. Okay, till pi. So I will get the positive waveform of the power and so on like that. In that case, the voltage is negative but the current is positive. So that the power we will get is the negative power. And again like that. So at the every 90-degree interval, we will find out that we have the identical shape for power which situated in positive and negative side. Okay, so same value of the positive and the same value of the negative, both the shape is identical. So in general, I calculate the average, I will get the 0. That's why the power is equal to 0. Okay, in the case of the pure inductive circuit. Okay, so basically this implies that average power consumed by the inductor, okay, this is the consumed by inductor is 0. Okay, and however, the instantaneous power pulsate at double the supply frequency as shown in figure here. Okay. So it may seen from the power curve that instantaneous power is positive when polarity of V and I are the same, and it is negative when the polarities of V and I are opposite. You can see that here both are the negative and both are the positive. Okay. So physically positive power means storage of electrical energy in the form of magnetic energy. Here the positive power is showing that the storage of, I am writing here, positive power meaning storage of electrical energy in the form of magnetic energy. Okay, so this we can say that this is the building up flux, building up flux, okay, around the inductor. And the negative power meaning, the negative power meaning is that release of magnetic energy, magnetic energy, which is we can say that the collapsing flux stored around the inductor back to the system. Okay, so thus that's why the average power is equal to 0. Okay, so this is the basic concept while the pure inductive circuit is connected across the AC source. Okay, so thank you very much. Please like and subscribe our channel.